So in this video, I'm going to solve some problems out of the textbook that correspond to the topics that I identified as being eligible for the final exam. And again, because it's eligible doesn't mean it's a guarantee, but it's something you ought to know how to do. So the very first topic I listed was finding the area between two curves. And so here is a problem out of the book. These are the review problems from chapter 6, I believe, the applications of integration. And this one is number 27. And I'm not going to do the whole problem. I'll just find R3. So I want to find an integral whose value is the area of the region R3. Okay, and if we could do that, we could certainly do all the rest of it. And then maybe we'll follow up with a volume question. So, number 27. So I want to find the area, this blue area, and notice we need to know the coordinates of this point right here. And you can tell from the graph here, almost certainly the coordinates are x equals 1, y equals 2. You know, if it wasn't that obvious, if we didn't have a scale there to read those, we could just solve the equations. One of the equations, the line here is 3 minus x, and we could set that equal to the red curve, 2 square roots of x, and solve for x. That wouldn't be too difficult. But because the grid is there, we'll take advantage of it. And notice if I integrate with respect to x, I can use one integral. So I move through this in the x direction. Everywhere the red curve is on the top, the line is on the bottom. So the boundary functions never change. If I were going to use functions of y, then I would have to switch integrals around this horizontal line. Below, actually we just have a triangle. You could use the area formula for triangles there, but then we would need an integral for here. So neither one is particularly difficult. But we'll use functions of x. I mean, it's probably what we would prefer to do. So the area is equal to the integral. And again, with this point being fairly obvious, we're going to integrate from 1 to 3. The function on top is 2 square roots of x. And the function on the bottom is 3 minus x. And so there we have it. The integral. The problem, 27, it actually, you can see down here, it asks us to find the area, but I'm going to trust that you can evaluate that integral. And so we'll leave that for you to do on your own if you think it would help you understand. Now, just in case this point wasn't given, let's think about this point right here, the intersection point. It's where the red line, 2 square roots of x, meets the diagonal line, 3 minus x. And so we need to solve that for x. We can do it algebraically. It's not too unusual for textbook problems to be simpler to solve, and I can tell by looking at this that one solution is x equals 1. Not by looking at the intersection they've identified here, but just looking at this algebra. If x equals 1, it's clearly both sides are equal to 2. Now, if we couldn't see 1, then we would square both sides. We would get 4x on the left. And when you square the right-hand side, there is a middle term. We get 3 squared, and we get minus 6x, and then we get plus x squared. So I have a quadratic equation. Subtract the 4x over, and it looks like x minus 10x plus 9 equals 0. So just move the 4x over, combine it with the minus 6. You move it by subtracting. And then we get a factorable expression, x minus 9 times x minus 1. So there are actually two solutions. One of them is obviously the one we want. We don't want the solution x equals 9. But we do want the solution x equals 1. So, area between curves. The function we integrate should really never be complicated. The function on top minus the function on the bottom. If we're using functions of y, then top is to the right, bottom is to the left. It would be a good exercise maybe to see if you can describe this area, R3, using functions of y, and then you could take it one step further and actually do the integration and see if you get the same answer. I think next I want to do the very next problem. It looks to me like number 28, so let me clear my slot here. All right. So number 28, find the volume of the solid, there we go. The solid obtained by revolving region R1 about the x-axis. So region R1 is this red guy over here, and we're going to go about the x-axis. So when I look at that region, I see everywhere there is a single function on top, the line, and everywhere there is a single function on the bottom, the red half parabola. So I'm going to use functions of x. We're going around the x-axis. That means I'm going to use the disk/washer method, and it actually is washers. For every x value, we already found the x coordinate of this point, 1, if we couldn't read it from the picture. And so for every x value between 0 and 1, we get disks that go from the line down to the half parabola. And this will probably make a really ugly picture, but if I could kind of draw those disks, there's one of them. Okay. That's not a very pretty picture, so I'm going to get rid of it. Whether we can draw a pretty picture or not, we can find the volume. It's pi times the integral from 0 to 1. The area exists from 0 to 1 out here. Disk washer, the constant out in front is pi, so we got that there. And then we just integrate. Because it's disks, we take the function on top, 3 minus x, square it, and then take the function on the bottom, 2 square roots of x, and square it. And there is the integral. And again, the problem asks us to actually find the volume, but that's an easy integral. We even get the square root away. So I'll let you evaluate it if you think that's something you need to do to study for the exam. Okay? Let's take the region R3. This is probably one of these. Notice that this region is used for problems 27 through 33, and this may be one of them at the top of the page over. It's up here somewhere, not in my photograph. And so I'm just going to make it up. So we're going to take the region R3 and we're going to rotate it about the y-axis. Okay, let me get rid of the problem we just solved. And here's the new one. We're going to rotate about the y-axis. And that may be, like I said, one of the problems up here, 29 or 30 or 31, whatever. We can solve it. And again, we're just going to find an integral. We're not going to evaluate it. R3, just like when we found the area over here, we really like to think of it as using functions of x. And since it's going around the y-axis, so let's record that. But we want to use functions of x, then we're going to use the shell method. So the volume is 2 pi. The integral, R3, because it's around the y-axis, but we're using the shell method, we're going to integrate with respect to x. So our variable for the integral is x. So the shell method, first of all, the x's on region R3 go from 1 to 3. And then we have x, the radius, representing the radius. And then we have, we need for each x between 1 and 3, we need to know how tall the shells are. And they're going to go from the parabola to 2 square roots of x down to the line 3 minus x. And that'll do the job. All right, again, easy to evaluate, not really what our focus is here. So there are other problems, like I said, this goes 27 through 33. I don't know which one I did here, if it's even one of the ones up above, but there are 29, 31, and 33, 3 odd-numbered problems that you can work on. These are all on page 479. Like I said, the review problems at the end of chapter 6. All right, so good luck on those. All right, next up is a problem, an integral, an antiderivative problem, and it's going to illustrate a couple of things. First of all, let me show you the integral. Well, this is kind of like a problem in the book, although I'm tweaking it a little bit. X inverse tangent of x. And if you think about the techniques that we've learned, there's only maybe 4 of them eligible for the exam. You can quickly decide that there's only one of them that has a chance here. If I had a square right here, then we could just do an ordinary substitution. We could let u be x squared and then du is 2x dx and everything would be wonderful. But there's not a square there. So I can't really relate, let me erase part of my x. I can't really relate anything here, inverse tangent of x, to its derivative to x. It's like 2 totally independent functions. And so that says, we've got to do it by parts. So that's what we're going to try. And then something interesting will happen along the way. So I think there's really only, well, let's think about this. I don't know the antiderivative of inverse tangent. I think we worked it out. Probably you wouldn't have it on your 3x5 card either. So I'm going to kind of go against the rule here and put the inverse tangent on my u, and then we'll put x, which kind of violates one guideline, and that is we like, power functions, polynomials like x here to be on the u because we drive the power down. But that would require me to move the inverse tangent over there, and then I would need to integrate, and I'm too lazy to look it up, and I think I can make it work this way. So here we go. du is 1 over 1 plus x squared. We know the derivative. We use it all the time. And therefore, v is 1/2 x squared. So this integral is equal to uv 1/2 x squared inverse tangent of x minus, and here's the big trade-off integral. We've got a 1/2 here. Let's push it through the sign. And then I have x squared over 1 plus x squared. So take a close look at that. It's an improper rational function. The degree of the numerator, they're both polynomials, top and bottom, and the degrees are the same. So let's do a quick long division. And then I'll show you a faster way to do this particular one. So x squared goes into x squared one time, and we get x squared plus 1. Subtract the x squareds go away, we get minus 1. That is of degree 0. That's less than degree 2, so we're done. And let's write our answer over here. So this first chunk comes along for the ride. And then we have this minus 1/2 out in front. And then we get the integral of 1, right, the whole part of our long division, and then we have a remainder of minus 1. And now we know all the parts of that, antiderivative-wise. So this piece still hanging out. And then I have minus 1/2. The antiderivative of 1 is x. And 1 over x squared plus 1 is the inverse tangent of x. And for good measure, let's write a plus c. So there is our answer. Circle it in red. That is this antiderivative. Okay, so we got to do two things here. We got to integrate by parts, and then we got to remember how we handle improper rational functions, both of which I think is a really good chance you'll see them on the final exam. All right, and I promised you another way to look at this integral right here, so let me clean things up. Boom. And let's take a look at just that little piece of it. So we have x squared over x squared plus 1. I guess we're doing it in red. All right, I'm not sure this is a technique. It's called thinking. And because it's not like a technique, it's not section 3 in chapter whatever, I didn't learn it. I didn't learn to think this creatively, this sort of independently. But years and years ago, I had a student who his high school teacher had showed this trick to him. Or maybe he dreamed it up on his own. He was a really good student. He eventually got a PhD in engineering. And here's what he showed me to do, which it does the same thing as long division. It's just easier. And that he said, okay, let's take our x squared, which we have, and now I'm going to add 0. When you add 0, like nothing really changes. So 1 minus 1. And then, let me change to a green. Now we're going to break this function up, into 2 separate pieces. That piece, and then in yellow, this piece. So let's go back to black here. Black, I said. So this integral is equal to, notice the green circle, x squared plus 1 divided by x squared plus 1. That's just 1, a number divided by itself. And then I have the yellow part, I have this minus, and then I have a 1 over x squared plus 1. And you can see that's exactly what we got after we long divided. So it's just a shorter way, if we can do it. When you look at this, and maybe you can see this nifty little trick, and then we're going to get x minus the inverse tangent. Sometimes you can do that, and it's kind of nifty when you can. You don't have to do it. Like I said, I never knew it when I was an undergraduate. I just couldn't think that creatively on my own. But once the student showed it to me, it's like, aha, I should have been able to see that. All right, there's that problem. Let's find another one. All right, so here's a problem modeled loosely on number 92 on page 595. This problem, number 92, is a little more complicated. We're going to do a simplified version, which is evaluate the integral from 2 to infinity, 1 over x log squared of x. All right, so you can see it's an improper integral, the first type. So what we're going to do is convert it to a limit. It's the first thing we need to do. The limit as b goes to infinity. The integral from 2 to b, 1 over x, ln squared And then for an antiderivative, hopefully, you can see a really good thing. That is, I have this log squared here, and sitting right here, let me do it in red, is the derivative of ln x. So that's my key. If I let u be ln x, then du is 1 over x dx. And so we get, coming from this limit over here, the limit as b goes to infinity. The integral, when x equals 2, u equals ln 2. And when x equals b, u equals ln b. And then we get the log squared, which is 1 over u squared. And then the 1 over x circled in red with the dx is simply du. Okay. Beautiful. That's an easy integral. So we'll go from ln 2 to ln b, u to the minus 2. Set it up for an antiderivative, and that is the limit as b goes to infinity. Raise the power to minus 1, divide by the new power. Evaluate from ln 2 to ln b. So this minus 1 right here, we can take it through the sign, just changes the sign, back to black. And then we get the limit as b goes to infinity. Because of this minus 1 power, we can reciprocate. Let's go back to black. And so we get 1 over ln b minus 1 over ln 2. Right, just plugging our limits into our u, thinking of u to the minus 1 as 1 over u. And so, back to black. As b goes to infinity, so does the log. Because it's in the denominator, this term goes to 0. This is a constant, this other term over here. And so we get 0 minus, come on, 0 minus 1 over ln 2. Gets us running out of space equals, let's do it right here, 1 over ln 2. And I'll circle it in red. And just for fun, I'll circle it in blue. 1 over ln 2. This integral equals 1 over ln 2. All right, that was a good problem. Two things it illustrates. One, how to deal with the improper integral. We convert it to a limit. And the second thing is just the antiderivative. You know, we see this ln squared, and then we can see right there, circled in red and now blue, the derivative of ln x. That's the key. So a straightforward substitution, which actually is an integration technique we learned in Calc 1, but always comes in handy. All right, let's find another problem. All right, here we are, chapter 10. As you know, if you watched this morning's video, that a topic that is eligible for the final exam is information about the sequence of partial sums. And let's work through a couple here. Let's see. Let's do number 63. We'll do it first. And so you can see the series. Sequence of partial sums means we add some terms, so it's part of the series. So S1 for number 63 is 4. Not sure why I'm using blue, but I guess I am. S2, 4 plus 0.9. 4.9. S3. So I could sum the first three up, and that's really easy to do for this one. But I think a better way to think about it in general, and maybe one of these other ones will give us a better example, is to get a new term, S3 of the sequence. We'll take the previous term, which is 4.9, and we'll add the next term to it. So right here is the sum of the first two terms, and to get the sum of the first three, we just need the third term. That's 0.09. And you can see that makes 4.99. Hope you can see that. Let's go to black. No, the text is black. Let's go to red. Maybe it'd be easier to see. Finally, it says find the first four terms. So we only need one more, and S4, well, it's the sum of the first three, 4.99, plus the next term down, which is 0.009. And so I'll write it down here in this open space, 4.999. And I'll bet you that that series converges to 5. So it asks for, I'll do it in green, for the first four terms. So here we go. There's the first one, second one, third one, fourth one. Bingo. Okay, let's do another one. When the terms are written out like this, you know, maybe it makes it feel a little too easy. So let's cancel this out. And we'll go to a new one. Let's do 66. So notice the sum starts at 1, so S1, back to black, equals the cosine of pi. Cosine of pi is -1. S2 is the first term of the sequence of partial sums, plus the next term, which is the cosine of 2 pi. And cosine of 2 pi is 1. So the second term of the sequence of partial sums is 0. S3 is the sum of the first two, 0 plus the third term, which is the cosine of 3 pi. That's -1. Equals -1. And finally, the fourth one. It's the sum of the first three, -1, plus the cosine of 4 pi, which is 1. So again, it asks for the first four terms, and here they are. There's the first one. There is the second one. There is the third one. And there is the fourth one. And probably you can find any particular term. They're just going to oscillate between -1 and 0. So this series actually diverges, but that's not what they're asking. Oh, they are. Then make a conjecture about the value. So the first example, I think we said it probably converges to 5. That's our conjecture. This one, we think it diverges. Because the sequence of partial sums, it doesn't blow up to infinity, but it doesn't approach a value either. It's just -1, 0, -1, 0, on and on and on, -1, 0, -1, 0, no limit. So almost certainly, not almost certainly, it diverges, period. All right. So one more question on the sequence of partial sums. This probably is better than the previous two. I just didn't see it before I worked the others. That's okay. We can do more. More practice is better. So here we go. This one's just a little more interesting, not so trivial. So the instructions are the same. Number 67, page 649. Part A, find the first four terms of the sequence of partial sums. So here we go. We'll do it in black. The first term I get by plugging in k equals 1. So we get 2 divided by 1 times 3. Right? 2 minus 1, 2 plus 1. So the first term is 2/3. The second term is 2/3 plus the second term. So when k equals 2, still got a 2 on top. And down below I get a 3 times a 5. So, if we do the arithmetic, common denominator is 15, I get 17. Multiply by 5 to get a common denominator, 10 plus 7. S3, 17/15, the sum of the first two, plus the third, which is 2 divided by, when k equals 3, we get 5 times 7. So you can see what's going on in the denominator. We're getting, do it in green, consecutive odd numbers, working our way up. Okay, and now if we do the arithmetic, it's kind of messy. Common denominator is 85, I believe. 15 times 7, no, 105. So I get 17 times 7 plus, this is over the 7 needs the 3, plus 6. Into space. If I do the arithmetic, if I ask this on the exam, might be a waste of time to ask you to do the arithmetic. 17 times 7 is 119. I believe we get 125s, 5 105ths. And for good measure, we can take the 5 out of that. We get 25 over 21. If my arithmetic's right, it may not be. You could pull a calculator out and check it. The concept is right. And now S4 is equal to the sum of the first three, 25 21st, plus the fourth term, which is 2 over 7 times 9. Just work our way. I didn't even look at the formula. I figured out, what's going on, consecutive odd numbers. And since we just had 5 and 7, we have 7, 9. But you can see, plug in 4, and that's exactly what you get. All right, I'll let you do the arithmetic. And we're done. Find the first 4. Here's the first one. Here is the second one. Here is the third one. And there is the fourth one. Sequence of partial sums. All right, number 19. Actually, let me do 18. I'll save 19, an odd number you can do when you're on your own and you can check your work. On page 668. The topic here is geometric series. So geometric series we should feel super comfortable about. We know everything about them. There is no mystery. They converge. And if we know the series is geometric, then we know there is an R value, the ratio. If that value is between -1 and 1, then the series converges. And if it converges, we can find exactly the number it converges to. Number 18, we'll do a few of these. Summation k equals 0 to infinity, 2/5 to the k. This is about as easy a geometric series problem as we could ask for. It is clearly geometric. R equals 2/5. The sum starts at 0, no tricks there. Remember our formulas, once we're convinced it's geometric, then we have this kind of shortcut formula, the first term over 1 minus r. So to find the first term, let me clean this up over here a little bit. K equals 0. So the first term is 1. The ratio is 2/5. Multiply top and bottom by 5. And we get 5/3. Distribute the 5, and then the 5's cancel. 5 minus 2. And there's our answer. Let's do number 20. So this one's a little bit different. It's written out rather than in sigma form. 2 plus 4/3 plus 8/9 plus 16/27 and so on. So without the algebra we had here, it's not so obvious maybe that it's geometric, but if it is geometric, then there is a value r that when I multiply it, it moves me from one term to the next. So if this series is going to be geometric, the thing that you multiply 2 by to get the 4/3 is 2/3. And let's check. So I'm just kind of thinking to myself here, I'll put it in parentheses, 2 times 2/3 equals 4/3. And if I multiply 4/3, that term by what I'm thinking is r 2/3. Notice I get 8/9. Perfect. And if I multiply 8/9 by 2/3, then I get 16/27. Yeah, so, 16/27, 8/9, 4/3. So this is a geometric series. R equals 2/3. And so it converges to, well, here's where this form comes in handy, because right there is the first term. We'll take 2 and we'll divide by 1 minus 2/3. Let's do it in black. Well, let's erase first. So first term over 1 minus 2/3. That's the right answer. We can make it pretty, multiplying by 3 to cancel out that compound denominator. And we get 6 over 1, 3 minus 2. 6 is our answer. So number 20 here. It is a geometric series. R equals 2/3, and it sums up. So this thing up here is equal to 6. It converges to 6. All right. And one more. This one is number 36. Same page, page 668. So just as a word of advice, if I think number 36 on page 668 is a good problem for the exam, then, probably all of the problems near it, number 35, number 37, number 34, so on, those are probably good problems too. So these are starting points for you. And here we have k equals 1 to infinity, minus e to the minus k. So, is it geometric? Let's find out. The thing that maybe makes it not quite fit the form of geometric is this minus sign right here. Geometric, the formula looks like a times r to the k. But we can deal with that algebraically. We can just drop the formula there into the denominator, and I'm going to get something like this, minus 1 over e to the k. Okay, so take a little bit, look at that, make sure that makes sense to you. The e to the minus k's 1 over minus e to the kth, and then I just pulled the kth power out of the whole thing. So it is geometric. R is negative 1 over e, which is between negative 1 and 1, so it converges. And we know what it converges to. We can find it. The first term, so to get the first term, take a look at where k starts, and we get minus 1 over e. Now let's go back to black. First term, black, he said. Minus 1 over e over 1 minus 1 over e. Right. R has a negative built into it. And now let's multiply top and bottom by e. And so I get negative 1 divided by e plus 1. Right, distribute this e out. That gets me e, and then the e's cancel here, and the minus signs cancel. So this series converges to that number. Bingo. All right, at the risk of maybe boring all of us, I've chosen one more sort of geometric series. And here it is, number 84. Now I say sort of, it really is not a geometric series because of that right there. Okay, I cannot write this series in the form that a geometric series needs. But as long as these individual series converge, I can distribute my sigma across. So what we're going to do is assume they converge, and we'll distribute sigma. And then if at some point we discover they don't converge, then we'll have to back up. But I think we're going to be just fine. So let's say equals, and I'll put a question mark. And then we're going to break it into two separate series. K equals 0 to infinity. 1/2 0.2 to the k. Plus summation k equals 0 to infinity. 3/2 0.8 to the k. So if you look closely at both of those, once we distribute the sigma, they are geometric series. And R, 0.2 less than 1, 0.8 less than 1, they both converge. So we're good. So let's circle the question mark and say, no problem. We're good to go. And now we can just use our formula. The first term, if k equals 0, 1/2, 0.2 to the 0 is 1, so the first term is 1/2. And 1 over, I'm going to write 0.2 as 1/5. I like fractions, maybe you don't, that's okay. I'm going to leave a little space here. Actually, I can do it right now while we're going. So just like we always do, I'm going to simplify that. I'm going to multiply by 10 over 10 because we have denominators of 2 and 5. And then this guy over here, the first term is 3/2. And 1 minus, and I'll write 8/10 is 4/5. And again, we'll multiply by 10 over 10 to simplify it. And now we just have an arithmetic problem. I get 5, 10 times 1/2, and then I get 10 minus 2. Distribute the 10 times 1 is 10, 10 times 1/5 is 2. Plus, similarly, 15? 30 divided by 2, and then I get 10 minus 8. So 5/8 plus 15/2 makes how many 8s? 5 plus 60. 65/8. So this series converges to 65/8. And we did it. That's enough geometric series. I'm going to pause here. We've worked our way through at least one problem from most of the review topics, except for convergence tests. I posted a video on Foxtail, not done by me, but recommended by a student who found it helpful, and I'll just encourage you to watch that. It goes through all of our convergence tests, and in particular develops a strategy, maybe the way you could think about using them. And then on Monday, I'll work some more problems and post them here. Hopefully I can do them Monday morning and have them posted by about noon on Monday. And this will be starting with where we left off here, except that I don't think I will do any convergence tests, or maybe I can do one or two where I use the strategy suggested by that other video. We'll see. But this will give you some things to work on over the weekend in case you're bored. All right, talk to you later.